Okay, let's dive together into a journey through the intriguing and somewhat peculiar universe of Albert Einstein, a name that resonates throughout history not only as an icon of science, but as one of the greatest geniuses to have walked among us. But what really makes Einstein such a fascinating figure? Well, apart from his iconic tousled hair, Einstein gave us not one, but two theories of relativity at the beginning of the 20th century, each more revolutionary than the other. Let's start with the theory of restricted relativity. Just imagine, it tells us that the speed of light, that electromagnetic field that illuminates our days and nights, is constant, no matter how fast you're moving. It may sound strange, right? You could be running at the speed of light, if that were humanly possible, of course, and the light would still be moving at the same speed as you. The universe has a way of making us question our own perception of reality. And it doesn't stop there. Restricted relativity also brought us the idea that the laws of physics are the same, whether you're in a rocket cutting through space at impressive speeds, or just shopping in the supermarket. Doesn't that sound a bit revolutionary? Yes, but Einstein, with his characteristic humility, said that restricted relativity was a good idea, but not something of genius. Well, I have to disagree with him here. This modest thought makes you wonder, what really defines a genius? Einstein believed that if he hadn't come up with the theory of restricted relativity, someone else eventually would have. The ideas were already in the air, so to speak, being debated by other physicists at the time. But wasn't it Einstein who tied them together, offering us a new way of understanding the cosmos? Imagine yourself floating in space, looking at the universe around you. Everything seems peaceful and majestic, doesn't it? But what if I told you that everything you see, all this stellar beauty, is influenced by something we can't even see properly? Yes, I'm talking about gravity, that mysterious force that keeps our feet on the ground and makes apples fall from trees. Classic Newton, right? But wait, Newton? Yes. Isaac Newton was the guy who explained gravity to us, and for centuries, we all thought he'd got it right. But then, at the beginning of the 20th century, along came a guy with messier hair than yours on a Monday morning, called Albert Einstein. Einstein looked at Newton's laws and said, "Very good, but what if?" And that's when everything changed. He introduced the theory of general relativity, a real game changer that turned our understanding of gravity upside down. Instead of just an invisible force pulling on things, Einstein showed us that gravity is the curvature of space and time around massive objects. Like, the Earth isn't just pulling the apple down, it's bending the space around it, and the apple is simply following the path of that curved space. Crazy, right? Now you might be thinking, okay, but did I really need something else to break my head apart from my favorite TV series? And the answer is yes. Because without general relativity, many of the things we take for granted today wouldn't work. I'm talking about GPS, satellites, and basically any technology that depends on a precise understanding of time and space. But the most incredible thing of all is to think that maybe, just maybe, if Einstein hadn't come along, we'd all be lost, literally, without a proper understanding of how to navigate our own planet. And to think that all this came from the mind of a man who, by his own admission, didn't wear socks. If that's not a reason to arouse your curiosity, I don't know what is. So, restricted relativity has an idea that sounds like something out of a science fiction movie. Space and time are not two different clubs, but members of the same team called space-time, with its 4 dimensions, 3 of space and 1 of time. This means that if you decide to run a little faster than normal, you not only move through space, you also move through time. Yes, that's right. Traveling in space can make you play with time, like when astronauts orbit the Earth at very high speeds and return home a little younger. Crazy, right? But calm down. It's nothing that will make you lose sleep. The difference is very small. Now, hold your excitement because we're going to the big show of the evening, the theory of general relativity. Its purpose? To tell us how matter, like us, planets, stars, moves when gravity is around and, what's more, how matter itself creates this gravity. Before we go any further, let's clarify a couple of things. What is this movement and what is gravity? And before you think about running away, I promise, it's going to be more fun than your high school geometry classes. Imagine going down a giant toboggan run or handling an old cell phone, because seriously, I'm going to try to make this as interesting as possible. So what Einstein did with general relativity was basically say, you know that gravity Newton talked about? So it's about more than an apple falling on someone's head. It's about how giant objects, like planets and stars, bend the very fabric of space and time. It's as if the universe were a trampoline, and each planet or star a bowling ball, making a curve right where it is. And we're like the smaller balls rolling towards the curvature. Have you ever stopped to think about what movement really is? No, I'm not talking about when you run to catch the bus that's already leaving the stop. I'm talking about something that goes much further, something that connects every particle in the universe. Just imagine everything that moves, from your smartphone falling off the table to the Earth revolving around the sun, follows very specific rules. And believe me, understanding this is almost like having superpowers. But first of all, remember this magic formula. Force, nós mass, x acceleration. It's the key to unlocking the secrets of movement. Let's explain it very simply. Let's say you're in an elevator. You're there calmly until suddenly the cable breaks. You and the scale, which was just there marking your weight, start to float. That's right. In free fall, you and the scale are like astronauts in space, with no weight at all. And here's the trick. In this situation, you have no way of knowing whether you're falling or floating in space. Einstein used this idea to come to the conclusion that gravity is actually acceleration. That's right, acceleration pure and simple. You don't need any force for an object to accelerate. It just needs to be in the right space-time, doubled by the surrounding masses, such as planets and stars. It's as if the universe were a big amusement park and gravity, the tracks that guide the carts, us and everything else that has mass, along the right path. But how is this possible? How can something accelerate without forces? Einstein's answer was geometry. Yes, the same subject you may not have paid much attention to at school is responsible for all of this. Space and time curve around massive objects, and we simply follow this curvature. Hey, have you ever wondered what it would be like to make an old cell phone take a radical 20-meter dive? You have two options. Either let the poor thing free fall, which is definitely not a good idea, or send it down a chute into a refreshing pool. At first glance, it might seem that the only difference between a somersault and a fun slide is the temperature of the waiter at the end. But in fact, what really changes the game here is geometry. Yes, that subject you swore you'd never use again after school. In Einstein's universe, gravity isn't just an invisible force that stops you flying when you stumble. It's much more poetic. Gravity is like the cosmic toboggan that guides everything, from old cell phones to planets and galaxies, through the universe. So the next time you see a shooting star, think of it as a little ball sliding down the biggest slide you can imagine, all because of the curvature of space-time. And speaking of space-time, imagine a stretched-out sheet. If you put a bowling ball in the middle of that sheet, it would sink, right? Now, if you roll a marble, it will move towards the bowling ball, not because it knows it's there, but because it's simply following the curvature of the sheet. This is Einstein explaining that we don't need mysterious forces to understand gravity. It all comes down to the geometry of space-time. According to general relativity, everything, from the jumps of old cell phones to the orbits of planets, doesn't need a magical force behind it. It's all a question of following the path that space-time gives us. That is, matter tells space how to curve, and the curve of space tells matter how to move. It's as simple as that. Einstein not only revolutionized the way we see the universe with this idea, but he also predicted things that sound like science fiction, like black holes and wormholes. It's as if he had given us a pair of special glasses to see the universe in a whole new way. I'm Paul Edward. Thank you very much for embarking on this journey with me. Until next time, and don't forget to look up at the sky from time to time. Who knows what else we might discover together?